Something that really confused me in organic chemistry was oxymercuration. And oxymercuration is the addition of water to an alkene, which involves treatment with mercuric acetate and water, which is then followed by a reducing agent like sodium borohydride. This is a two-step process, and the first step is when the alkene is first treated with mercuric acetate. Then the initial alkyl mercury compound formed is then reduced by sodium borohydride. The mechanism's regiochemistry is Markovnikov addition, meaning that the final product will be the Morse substituted alcohol. Also, in the first step, there's formation of a cyclic mercurium ion, which is similar to a polonium ion, which we've seen before. So there are no carbon cation rearrangements in this mechanism. And lastly, the reagent sodium borohydride replaces the mercury with hydrogen, meaning that is removed by reduction to give the final alcohol. So I will show an example, and just a generic overall example to show how the mechanism works is something like this molecule here. When treated first with the mercuric acetate and water and sodium borohydride second to replace the mercury group with hydrogen, gives yield to this product here, and you can see that the alcohol group is right here. So a more generic way of showing this would be something like if you have an R group, something like that with your double bond. And if you want an alcohol group, you can treat this with mercuric acetate and water right here. And then secondly, your reducing agent of sodium borohydride. And this would give yield to a product like this, where you have your R group, and it would go to the more substituted side of the double bond, which was right here. So the more substituted side would be here since you have this R group. So your alcohol group would be something like that right here. So something that helped me really understand how this mechanism works was kind of just rewriting it over and over again and understanding how the curved arrows worked. So I will show an example of that. And here, if you start off with a molecule like this, and you treat it with your mercury acetate, so there's two of them, and this has a lone pair right here. So first, the lone pair on the mercury would go down to the carbon. The bond connecting the mercury to the acetate would go here to the oxygen, and the double bond would go back to the mercury. So you can see how this would form the mercurium ion. So this gives yield to this molecule here, where you have your mercury group. This goes down like this, and you have your other acetate group still right here. And this has a plus charge since these two electrons in the previous step went down to that carbon. So to get rid of that positive charge, you take this bond and it breaks off to the mercury here. And in the next step, the H2O, the lone pairs here, will go down to the carbon. So then you have this product here. And you have your OH and your H, which has your lone pair. But this obviously is not, it is octet, so this has a charge right here. So then, to get rid of that charge, you would break this bond between the O and the H. And in the following step, the H2O still has its lone pairs and will break off to the H here, and that's going to form H3O. So then, your final product would be your CH3, CH, CH2, whoops, HG, OAC, I'm sorry, that's a single bond here, and this goes down to your alcohol group, plus your H3O, plus that was from the previous step here. So basically, the oxymercuration is not that hard of a mechanism once you redo it a couple times and understand where electrons are going. And to finish the assignment, two other topics that I had a little bit of confusion with was RNS configurations, but to solve that I used my tetrahedral and assigned the priorities to different colors of the tetrahedral. And secondly was resonance structures, and how I fixed that problem was basically by doing a lot of problems over and over again to understand more about it. Thanks.